Now let's see the theorem which is supported from the previous theorem which we have discussed. So this also is an extension of the previous theorem to understand the further properties which are connected with quadratic equations and the signs of curves. So the change of signs here, let's start with the statement of the theorem. So the statement of the theorem states that let A, B, C be three real constants and A not equal to 0 such that the quadratic equation ax squared plus bx plus c equal to 0 has real roots alpha and beta with alpha less than beta then I'm going to prove that with these conditions of this quadratic equation having real roots alpha and beta with alpha less than beta, then initially I prove that for alpha less than x less than beta, that is when x lies between alpha and beta, we have ax squared plus bx plus c and a have opposite signs. So we have to prove here that when x lies between alpha and beta, then this expression and a will have opposite signs. Similarly, for x less than alpha and x greater than beta implies this and this have same signs is what we are going to prove. So there are two cases which we are going to prove here, whereas the case 1, when x lies between alpha and beta, this and this have opposite signs. When x lies outside of alpha and beta, then this and this have same signs is how we are going to prove. So let's see how we can prove that with the proof followed. So clearly it is given that a, b, c are real numbers and a is not equal to 0, then alpha beta are roots of ax squared plus bx plus c equal to 0 implies I can write ax squared plus bx plus c as clearly a times of x minus alpha into x minus beta, where I assume alpha is less than beta. So with the assumption that alpha is less than beta. So using this, we are going to prove the sign change, opposite signs and same signs connected with this. So let's see how we can do that with. Initially, to start with, let me reconsider the above expression in the form of by a is x minus alpha into x minus beta, because this is the expression which helps us in understanding the signs. Because we need to identify the opposite or same signs, we divide this with this, because the fractional representation helps us in identifying the same signs or opposite signs. So therefore we have obtained the expression as ax squared plus bx plus c by a is obtained as a times of x minus alpha into x minus beta, which I took as equation 1. Now using this, let's see how each of the cases can be proved for. So initially, to start with case 1, I have alpha less than x less than beta, that is x lies between alpha and beta. So using this, let's see how we can prove for this and this with opposite signs. So alpha less than x less than beta can be split as this and this in the form that alpha is less than x and x is less than beta. The first pair and the second pair are split in the inequality. Now here, this is alpha less than x implies x minus alpha is greater than 0, and x less than beta implies x minus beta is less than 0. So this proves that this is positive and this is negative, because greater than 0 and less than 0, and positive into negative is negative. Therefore, if I combine them, x minus alpha into x minus beta will be negative, because plus into minus is minus. We all know that property. Plus times minus is minus. So plus times minus is minus. So this being negative, we know that, oh, this is not a, but a is already here. We know that x minus alpha into x minus beta is indirectly this whole of expression. So in place of this, I substitute this, because these two are equal. Therefore, substituting for the left hand side, I get this to be ax squared plus bx plus c by a, which is less than 0. This is strictly from equation 1 is what I get. Now, this makes us clearly understand that if numerator by denominator is negative, that means both should be of opposite signs but cannot be of same signs, because if I have minus 5 over minus 3, this becomes positive, or 5 times of 3 also becomes positive. But if one of the sign is changing opposite signs, then it becomes a negative, or minus 5 over 3 also becomes a negative number. So with these examples, we assume that when this whole of the expression is negative, then numerator and denominator must be of opposite signs, as supported with these examples. That implies the expression and a will be of opposite signs is what we conclude. Assuming that x lies between alpha and beta, then this is the case. This and this will have opposite signs. Similarly, let's take the case 2 and see if we can get this to be of same signs or opposite signs. So proceeding similarly as case 1, let's continue with case 2. So let's take the case 2, which says that x is less than alpha or x is greater than beta is what we're going to consider and prove for the sign change. So initially, to start with x less than alpha, and finally with x greater than beta, I get x less than alpha implies x minus alpha is less than 0 is what we get here, and x greater than beta implies x minus beta is greater than 0 is what we get out here. Now let's see the case 2 where x is less than alpha or x is greater than beta, where I split initially with x less than alpha and then with x greater than beta, and see with each of the cases. Now, as I know that alpha is less than beta in either of the cases, let's initially proceed with this and see what exactly I get. Now, x is less than alpha and alpha is less than beta implies x is less than alpha less than beta. X less than alpha here and alpha less than beta out here. So with this, I understand that x is less than alpha and x is less than beta in case of this first case. Therefore, I get x minus alpha is less than 0 and x minus beta is also less than 0 in the initial case. Now let's see the second case of x greater than beta and alpha less than beta. So x greater than beta and x and beta, that implies I have this as beta less than x, but alpha is less than beta. So I have this to be when beta is less than x from this equation, x greater than beta, beta less than x, and alpha less than beta from here implies beta is less than x. Therefore, alpha is less than x. Therefore, in this case, I get two conditions: x is greater than beta and alpha is less than x. So are the two cases which I get here, such that when I simplify, I get x minus beta greater than 0 and x minus alpha is greater than 0, because alpha minus x is less than 0, x minus alpha is greater than 0, and this is greater than 0. So proceeding with this two cases of considering, initially I get both of them as negative and both of them as positive. Thus, when I multiply x minus alpha times x minus beta, when both are negative, the product of negative and negative is positive, because since minus into minus is plus. We all know that. This is positive and this is positive, so plus into plus is plus. Therefore, I get this x minus alpha into x minus beta is greater than 0 when I combine the product of these two, since plus into plus is the case here. Now, I try to substitute this for this and see that the two expressions will have same sign, because when I consider ax square plus bx plus c by a will either be positive or positive. In both the cases, this is positive or greater than 0 implies that when the numerator by denominator is positive, these two must be of same sign. Both must be minus or both must be plus. We cannot have 1 plus, 1 minus, or 1 minus and 1 plus. The possibility of this is positive implies an A will have same sign, is how we understand the quadratic expressions with change of signs. So therefore, for case 2 they have same sign, and for case 1 they have opposite signs, is how we understand. Now let's see the maximum and minimum values of quadratic function or a quadratic equation. Now in this case, we have a very deep relation between the sign of a, that is the coefficient of x square, which we denote with a, and the extreme values, that is the maximum and minimum values. Say for example, I take the quadratic function y equals f of x is general quadratic equation ax squared plus bx plus c. Then I always have a relation between this a, which is coefficient of x squared, and the extreme values, that is max and min of this function. The highest and the lowest value of this function is always related with sign of a. Decides the extreme values of the quadratic function, is how we understand the relation between sign of a and the quadratic function. So let's see through the supported theorem how the sign of a is related to the extreme values of the quadratic function, the max and min of the given quadratic function. So let's see the statement of the theorem supporting the sign of a and the extreme values. The theorem states that there are three constant real coefficients a not equal to 0, such that y equals ax square plus bx plus c. Then I had to prove that if suppose I have a greater than 0 implies, for this sign of a being positive in the first case, implies the quadratic function. So when a is positive implies the quadratic function y equals ax squared plus bx plus c has absolute minimum. So here we relate with a greater than 0, I get a minimum value, and for a less than 0, of course, with maximum value. Is how we connect this coefficient of x squared, that is a, with its sign related to minimum. A positive, function minimum; a negative, function maximum. So therefore, for the first statement which says that a greater than 0 implies the quadratic function y equal to ax squared plus bx plus c, the general quadratic function has absolute minimum. And not only that, to add with further property, we need to prove that has absolute minimum at x equals minus b by 2a, and I had to prove that my minimum value is nothing but 4ac minus b squared by 4a. So I need to prove that my minimum value is this, and it is minimum at x equals minus b by 2a. Are the two things which I need to prove in my part A of the theorem. Similarly, my part B has to be proved with stating that if a is negative, that is, if a is less than 0, that implies the quadratic function y equals ax squared plus bx plus c, as taken in the previous case 2, has absolute maximum. Here being absolute minimum, here it is absolutely maximum for a less than 0 and absolute minimum for a greater than 0. Has absolute maximum at x equals minus b by 2a, and maximum value is 4ac minus b squared by 4a. Is the same case as we obtain for the minimum condition, is what we are going to prove in the statement of the theorem. So let's start with the continued part of the proof of the above theorem. Now to start with the proof, let's start with the general quadratic function. So we have already considered the general quadratic function as y, which I represent as f of x, and which is nothing but ax squared plus bx plus c, with a, b, c being the real coefficients, and of course a not equal to 0. Now also we have seen that this quadratic function, when simplified in the previous theorem, was further simplified with the complete square form when I take a common as a times of x plus b by 2a whole square plus 4ac minus b square by 4a. Therefore, my f of x can also be further simplified into complete square in this form, as this was already proved in the previous theorems. So let me take this simplified form as equation 1, through which I am going to achieve the proof of the given theorem. Now, initially, to start with the first condition, I have a greater than 0. Therefore, let a greater than 0 and prove for the part A of the theorem. So when a is greater than 0, I clearly see here that from equation 1, I clearly see that a is greater than 0 and x plus b by 2a is also whole square is also positive. So this being positive since a is greater than 0, and this is positive since all squares are positive. Therefore, the whole of this term is positive because a greater than 0 and squares are greater than 0. So this into this is overall a positive value. Therefore, that implies f of x can be written as a positive value, some positive value which is not a fixed value out there, plus 4ac minus b squared by 4a. Now, as I also observe here, I see that this is the term independent of x, which I write separately out here. Therefore, I get a positive value plus 4ac minus b squared by 4a when I simplify through this and this, using the condition of a greater than 0, this being positive plus this. So this makes me understand that f of x is always greater than this because there is some positive value added to the given quantity. So which makes us understand that f of x should obviously be greater than or at the most equal to 4ac minus b squared by 4a, because there is some value, positive value added to the quantity this for getting f of x. Therefore, this must always be greater than this always being smaller quantity than f of x with positive value added out there. So this is greater than or equal to this is what we get in the initial case. So f of x is greater than or equal to this. Similarly, let's also continue with seeing what happens when I take x equals minus b by 2a. This is strictly greater than, and I will also prove for equality condition in the second case, for which I take this as equation 2, where I have proved that f of x is greater than 4ac minus b squared by 4a. Let's take equality condition in the continued proof. Now let's take x equal to minus b by 2a. For x equals minus b by 2a, now substituting in 1, I get f of x is 4ac minus b squared by 4a, which I get through substitution of x equal to minus b by 2a in equation 1. Now, when I see equation 2 and 3, I see that from equation 2, I have f of x. Therefore, when I combine equation 2 and 3, I get from 2 and 3, f of x is strictly greater than or equal to 4ac minus b squared by 4a is what we get. Now this makes us clearly understand that the y value at the most is greater than or equal to this. That means this must obviously be the minimum value, because any value you take for f of x, this always greater than or equal to at the most this. That means this acts as the least value for the function f of x. That implies 4ac minus b squared by 4a is the least value of the quadratic function ax squared plus bx plus c. Every other value is greater than or equal to this. This is the least, and hence this is the minimum value, which proves that implies f of x equal to 4ac minus b squared by 4a is the minimum value of the function of this, and it is minimum at x equal to minus b by 2a. So this is how for a greater than 0, I get the minimum condition in this form, supported with the proof in the above theorem. So for f of x equals this is the minimum value of this, and x at x equal to minus b by 2a for a greater than 0. That is, this is the minimum value and the function is minimum at x equals minus b by 2a. So x value and y values at the minimum point are given by this. Therefore, when I write the minimum point ax square plus bx plus c for a greater than 0 is given by minus b by 2a and 4ac minus b square by 4a is how I write the minimum value of the function. Is given by these coordinates is how we understand this. So let's see how we connect this with the graph of the quadratic function. Now the part B of the theorem is using the condition of a less than 0, that is, what would be the case when a is negative. So when it comes to the part B, I assume that a is less than 0, that is a is negative, and see how we can proceed with the proof of this theorem. Now when I take a less than 0, I clearly see that this function has a less than 0 which is negative, all squares are positive, and then I have some quantity multiplied with this. But negative into positive is again a negative value plus this, that implies my y equals f of x will be a negative value plus the quantity 4ac minus b squared by 4a. So here I clearly understand that unlike the part A of the theorem where I got positive value plus the fixed 4ac minus b squared by 4a, in this case of a less than 0, I have negative into positive, which is negative value plus 4ac minus b squared by 4a. So when I add a negative value to the quantity, it obviously reduces. That means f of x is always less than or equal to this, because there is a negative value added but not the positive value. Adding of a negative value implies reducing the quantity by some units. So in this case, because we are reducing the quantity f of x by adding negative value to this, implies mathematically we have f of x is less than 4ac minus b squared by 4a, which I take as equation 4. Now as I see here, this is less than this. Let's see how equality can be obtained. What happens when I get equality? When, on what cases do I get equality is what we're going to see here. Now let's see what happens when x is minus b by 2a. So even in this case, I see that for x equals minus b by 2a, I have f of x equals 0 plus 4ac minus b squared by 4a, because this reduces to 0 when I substitute x equal to minus b by 2a, and this finally reduces to this by 4a, which I take as equation 5. Therefore, combining equation 4 and 5, I see that, therefore, combining equation 4 and 5, I clearly get f of x is strictly less than or equal to 4ac minus b squared by 4a. So this clearly makes us understand that every value of f of x is less than or equal to this. So this stands as the highest. So this implies 4ac minus b squared by 4a is the greatest value of the quadratic function ax squared plus bx plus c. So this is the greatest value when f of x is less than or equal to. That implies y equals f of x equals ax squared plus bx plus c has minimum value, the maximum value, because this is the highest value which it can reach. Therefore, this has maximum value at x equal to minus b by 2a, and the maximum value is given by 4ac minus b squared by 4a. Now this is when a is less than 0, is how we understand the concept of maximum and minimum connected with sign of A. When A is less than 0, I get maximum value, which is this, a maximum at this. And when A is less than 0, greater than 0, I get minimum value and then minimum at this. Now, interestingly, there is a very interesting question out there which says that how can the maximum value and the minimum value be same though when A is differing? In part A also we had the minimum value to be 4ac minus b squared by 4a, and even in part B we have the maximum value also 4ac minus b squared by 4a. Why do they not change is the biggest question. How can both values be same, maximum and minimum? It is because the sign changes the value as obtained. If A is greater than 0, this becomes the least value. If A is less than 0, this becomes the greatest value. As we do some exercise problems, we come to know on how this is understood as why it becomes maximum or minimum, though the formula is same, but the sign changes the maximum into minimum and minimum into maximum, is how we understand this concept. So finally, when I want to find the maximum point on the function, I can write this as for A less than 0, maximum point is given by minus b by 2a, 4ac minus b squared by 4a is how we understand the maximum and minimum of a function, the quadratic function. So continued with this, let's see how we understand this with the graphs. The graphical understanding of this theorem is equally very important because that makes us understand the concept more deeper. So let's enter into understanding the theorem through the graphical understanding. So let's connect the theorem with the graphical understanding because we need to understand this more through the graphs than the analytical or the algebraic solving. Now the theorem had two basic important cases. One is A greater than 0 and A less than 0. So let's divide the two cases of the theorem into one being that the quadratic function has A greater than 0 and the other is A less than 0. Now we all know that a quadratic function is a parabola. So a parabola which is either this or this shaped. So a quadratic function has the shape of a parabola. This is upwards and this is downwards, is what we discussed in the previous sessions of the quadratic function. Now since a quadratic function on graphing is a parabola, now clearly we know that if A is greater than 0, the parabola is downwards, and when A is less than 0, the parabola is upwards. So this is very important note we make, that in this case the parabola is downwards, and for this the parabola is upwards. So as I see this, I clearly see that now since the quadratic function is downwards for A greater than 0, I always see all the points which are going down are the least points, but as you go on to the top, the values start increasing and reach to the highest, which is the maximum value. So this is maximum when A is greater than 0. Now here we see that there are two cases. One is A greater than 0 and A less than 0, as we have seen that a quadratic function is a parabola when I graph either a parabola which is upwards or which is downwards, in this case being upwards and in this case being downwards. So we have learnt in the previous sessions of the quadratic equations and functions that when A is greater than 0, the parabola is always upwards, is how we connect the A with the quadratic function. And when A is less than 0, the quadratic function is downwards. It's a downward parabola for A less than 0, and this is an upward parabola for A greater than 0. Now as I clearly see here that the values are going on the top, so as we come down, the values start decreasing on the quadratic function. So therefore, as the values when coming down decrease, they tend to come to the least, which is the minimum value which is identified here. So this point will give me the minimum value. This is the minimum point, which is given by the formula minus b by 2a and 4ac minus b squared by 4a is what we get as the minimum point, in this case being a greater than 0. Now, as I switch on to the second case, I see that as the points are moving to the top, they reach, the values increase and reach to the highest, where this point is called maximum, because this has the maximum point, and thus given by the formula minus b by 2a 4ac minus b squared by 4a, which I get as maximum and minimum, is how I understand for the given quadratic functions. In this case, this quadratic has the maximum, in this case it has the minimum. This is how we understand the maximum or minimum based on a less than 0 and a greater than 0.